Second law of thermodynamics. Okay, the connections between the entropy and spontaneity of reactions is expressed by second law of thermodynamics. According to second law of thermodynamics, the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process, which is the entropy change in the universe, delta S universe, for any process is sum of the entropy change in a system, delta S system, and the surrounding, delta S surrounding, and mathematically can be expressed in a second law of thermodynamics. Okay, the second law of thermodynamics states that the process occur in a certain directions and not in any directions. Okay, from the second law of thermodynamics, we can explain the origin of the spontaneity and show how to define and measure and use entropy to discuss the spontaneous process. As well as we can also measure the Gibbs energy. Okay, the difference between the first law and second law of thermodynamics, which is the first law of thermodynamics, also known as a law of conversions of energy, which is state that the energy cannot be created or destroyed in an isolated system, while second law of thermodynamics states that the entropy of an isolated system always increase, which is it is impossible to completely convert heat into work, which is heat doesn't spontaneously flow from cold reservoir to a hot reservoir. First law of thermodynamics gives no clue on which process will occur and which will not, which is it does not tell the directions in which a process can occur spontaneously. Okay, the directions of the reactions can be obtained from the second law of thermodynamics. Okay, second law of thermodynamics. Entropy change in the system, which is delta S of reactions, is equal to the summations of the entropy of the products minus to the summations of the entropy of the reactant, which is M and N is stoichiometric coefficients, and this symbol represents the summations. Okay, consider the reaction between A and B producing C and D, which is delta S reactions is equal to the summations of the entropy of the products minus to the summations of the entropy of the reactant. Okay, if the change in entropy is larger than zero, means that the reactions produce more gas than it's consumed. Okay, for example, from the reaction here, which is there are no gas in the reactant side, while one mole gas in products. Okay, if the change in entropy is less than zero, means that the number of gas molecule diminish. Okay, for example, 4 mole of gas producing 2 mole of gas. Okay, and then if the change in entropy is more than zero and or less than zero, but the change is relatively small, means there is no net change in the number of gas molecule. Entropy change in surrounding, delta S surrounding. For exothermic process means that heat transfer from the system to the surroundings. Therefore, it will increase the number of microstates and entropy of the surroundings. In exothermic reaction, delta H is negative value and favor a spontaneous reactions. For endothermic process means that the system absorbs heat from the surrounding. Therefore, the decrease in entropy of the surrounding due to the molecular motions decrease. For constant pressure process, the heat change is equal to the enthalpy change of the system, delta H of the system. Therefore, the change in entropy of the surrounding, delta S surrounding, is proportional to the enthalpy of the system. Okay, for the exothermic reactions, the minus signs indicating that this is the exothermic reactions, and delta S is positive, indicating that there is the increment in entropy or the disorder of the molecule or atoms. For endothermic reactions, which is delta H of the system is positive, and the negative signs of delta S that ensure that the entropy of the surrounding is decreased. The higher the temperature, the smaller the delta S of the surroundings, and vice versa. Okay, as we know, entropy will increase with the temperature. Okay, an ordered system has a low entropy, and a disordered system has a high entropy. At high temperature, a certain amount of heat added to the system causes a smaller change in the entropy than the same amount of heat at a lower temperature. It is because if the temperature of the surrounding is high, the molecules are already quite energetic. So, when the absorption of heat from the surrounding for the exothermic process have a little impact on the molecular motions and result in increase in the entropy of the surrounding will be small. Okay, comparably, if the temperature of the apalah. So from the relationship, we can predict whether the reaction is spontaneous or non-spontaneous reactions. Okay, consider the reactions between the nitrogen and hydrogen producing ammonia. Given that the entropy of the system is equal to negative 199 J per kmoles and the enthalpy of the reactions is equal to negative 92.6 kilojoules. So delta S of the surrounding is equal to the enthalpy divide by temperature, so we can get this value, so that the total or the entropy of the universe is equal to the summations of the entropy of the system and entropy of the surroundings. Okay, from the result, we can see that delta S of universe is positive, means that the reactions is spontaneous at 25 degrees Celsius. Okay, the thermodynamics can tell whether the reactions is spontaneous under the specific conditions 25 degrees Celsius, but not related to the kinetic or reaction rate. Okay, as mentioned in previous slide, that for exothermic reactions mean that heat transfer from the system to the surroundings. Okay, means that the entropy will for the surrounding will increase. Okay, and then for the entropy of the system, which is heat absorbed from the surrounding to the system, therefore it will reduce or decrease the entropy of the surrounding. Okay, in order to express the spontaneity of the reactions more directly, the thermodynamic functions, which is called as a Gibbs free energy or free energy, is used. Okay, Gibbs free energy is the energy available to the works, and thermodynamic functions of Gibbs energy is given by this equation, which is delta G is equal to delta H minus 2 temperature times 2 change in entropy for the constant temperature process. S and G are state functions, which is when delta G is less than 0 means that the reaction is spontaneous in the forward directions, while if the delta G is more than 0, the reaction is non-spontaneous and the reaction is spontaneous in the opposite directions, which is more favorable to the reactant. Okay, so when the delta G is equal to 0, the system is at equilibrium, means there is no net change in the reactions. Okay, standard free energy of the reaction, delta G of the reactions is the free energy change for a reactions when it occur under standard state conditions. Okay, means that it's occur under 1 atm and 25 degrees Celsius. So when reactant is in their standard state, convert into the products in their standard states. So the Gibbs energy of the reactions is equal to the summations of the Gibbs energy of the products minus to the summations of the Gibbs energy of the reactants, which is M and N is the stoichiometric coefficients. Okay, consider the reactions A and B producing C and D, so that the standard free change for these reactions is given as a delta G reactions is equal to the summations of the Gibbs energy of the products minus to the Gibbs energy of the reactant. So the second law of thermodynamics tells us that the spontaneous reaction increase the entropy of the universe, which is delta S of the universe is more than 0. So in order to determine the sign of delta S of the universe, whether positive or negative, we need to calculate the delta S of the system and delta S of the surrounding, which is from this equation, when we substitute delta S of the surrounding with delta S of the system over temperature, so we can get these equations. Okay, then by multiplying both sides of the equation with temperature, then we can get these equations. So in order to make a reaction is spontaneous, so that delta H of the system minus T change in system should be less than 0. Okay, we want to change this sign from more than 0 to less than 0, so that we need to multiply by -1. So we'll get these equations. So that the Gibbs energy at constant temperature and pressure can be defined as delta G, change in Gibbs energy, is equal to change in enthalpy minus 2 temperature times change in entropy, delta S. Standard free energy of formation, delta Gf, is a free energy change that occurs when 1 mole of compound is synthesized from its element in their standard states. Standard states mean 1 atm and 25 degrees Celsius. When we applying the Gibbs energy equation, which is delta G is equal to delta H minus 2T delta S. Okay. For example, from the example 1, which is when delta H is positive and delta is also positive, means that it will give the value of delta G will become negative as high temperature. So means that the reaction is spontaneous at high temperature, while at low temperature, the value of delta G will become positive. So means that at low temperature, the reaction is non-spontaneous or spontaneous in reverse directions, which is it is more favor to the reactant. Okay, for the second equation, which is when the delta H is positive and S is negative. Okay, positive and then negative. So the delta G will become positive. Okay, means that reaction is spontaneous in the reverse directions at all temperature. Means that it is favor to the reactant. Okay, let's say you want to calculate the Gibbs energy for the following reactions, which is we consider that the reactions is occur at 25 degrees Celsius. So firstly, you need to calculate the enthalpy of the reactions, which is enthalpy of the reactions is equal to the summations of the enthalpy of the products minus to the enthalpy of the reactant. So delta H of each species can be found from the thermodynamic data. Okay, please note that you need to consider the state of the species because the value is different. Okay, for the solid, liquid and the gas. And then you need also calculate the entropy. Entropy is equal to the entropy of the products minus to the entropy of the reactant. So for the reactions carried out under the standard state conditions at 25 degrees Celsius is equal to delta G is equal to the delta H minus 2T change in entropy. So from that equations we can calculate the Gibbs free energy of the reactions. So from the calculations, delta G is large quantity. So we can conclude that the reactions is not favored at 25 degrees Celsius. So in order to make delta G is negative, so first we need to find temperature at which delta G is equal to 0. So means that the delta G become negative at the temperature larger than 835 degrees Celsius. Okay, for example, we choose 840 degrees Celsius and substitute in these equations. So we can find that the delta G is negative 0.8 kilojoule at 0°C or 1113 Kelvin to make the reactions is spontaneous. Okay, at the temperature at which the phase transition occur, that is at the melting point or boiling point, the system is at equilibrium when delta G is equal to 0. So the equation is become 0 is equal to delta H minus T change in entropy. So let's consider the transitions from the ice to water. So for the ice to water transition, delta H is the molar heat of fusions, so we can refer to the tables, and T is the melting point. So the entropy change is therefore is equal to delta S ice to water is equal to 6010 joule per mole over 273 Kelvin. So it's equal to 22 joule per K moles. Okay, thus when 1 mole of ice melt at 0°C, there is an increase in entropy of 22 J per K mole. The increase in entropy is consistent with the increase in the microstates from solid to liquid. Conversely, for the water to ice transitions, the decrease in entropy is given by delta S water to ice is equal to negative 6010 J per K mole divided by temperature 273 Kelvins. We can calculate entropy change in each case using the equation delta S is equal to enthalpy divided by temperature as long as the temperature remains at 0°C. Okay, the same procedure can be applied to the water to steam transitions, which is in this case delta H or enthalpy is heat of vaporization and T is the boiling point of the water. Okay, table shows the molar heat of fusions for the selected substance in kJ per mole. Okay, when delta G is equal to 0, means that the system is at equilibrium. So from there we can determine the temperature range for a spontaneous reactions. When delta G is equal to 0, we can also determine the melting point or boiling point, which is the phase transitions happen at equilibrium. Free energy and chemical equilibriums. In a chemical reactions, not all the reactants and product will be at their standard states. Okay, standard state means that the reactions occur at 1 atm and 25 degrees Celsius. Under the conditions that are not standard states, we must use delta G rather than delta G naught to predict the directions of the reactions. Okay, so delta G is equal to delta G naught plus RT ln Q, which is R is gas constant, so we use 8.314 J per K mole. T is the absolute temperature of the reactions, Q is the reaction quotient, and G is a Gibbs free energy under experimental condition, which is at equilibrium Q or reaction quotient is equal to K. At equilibrium, delta G is equal to 0 and Q is equal to K, where K is equilibrium constants. So delta G naught of Gibbs free energy at standard state is equal to negative RT ln K, which is K is constant, Kp is constant for gas, and Kc is the constant for solutions in the reactions. When delta G is less than 0, means that more products appear at the equilibriums. When delta G is more than 0, means that more reactant at the equilibriums. While when delta G is equal to 0, means that product and reactant are equally favored at equilibriums. Delta G measure the Gibbs energy under non-standard state conditions, which is used to predict the directions of the reactions, whether the reactions is spontaneous or non-spontaneous reactions. While delta G naught measure the Gibbs energies under the standard state conditions, it can be used to determine whether the product or reactant are favored when equilibrium is reached. gives free energy and chemical equilibriums. When Q is less than K, means that the reaction is forwards reaction spontaneous, which is favor to the products. When Q is equal to K, means that the reaction is at equilibriums. While Q is more than K, means that it will forward reactions for non-spontaneous, which is favor to the reactant. So the relationship between the Gibbs and the constant K, as predicted by equation delta G is equal to negative RT ln K. Okay, when K is more than 1, so ln K will become positive and delta G will become negative, means that products are favor over reactant at equilibrium. While when K is equal to 1, so ln K will become 0 and delta G also becomes 0, means that product and reactant are equally favored at equilibriums. While when K is less than 1 and ln K become negative and delta G will become positive, means that reactant are favored over products at equilibrium.